Swayam Prabha. Digital India. Educated India.
Good day to all of you. In the last class we looked at control measures for contaminated sites, more in the form of making vertical barriers around contaminated areas so that the contamination did not spread beyond what it had already. I mean the area which is occupied by the contaminant should not increase. Today we will look at some of the options for remediation. And again let me re-emphasize, remediation is a complicated task. You have to know all the chemical reactions which are involved between the water and the soil and the contaminant and the leachate, and how do you reverse those and how do you bring back soil to its original condition. So we talked about control and containment last time with covers and capping and vertical barriers and combinations, and today we look at treating. How do we treat the source, how do we treat the soil, how do we treat the pore gas, how do we treat the pore fluid, and how do we treat the groundwater. So the aim is if I have the source and if I have the contaminated site, then I have to treat and I have to treat or remediate. If everything is small, the tendency is let me excavate it and replace it with good material, local soil. If everything is large, then it is not possible to excavate everything and replace it with good material. Even if you excavate it, the good material that you are going to put back, is it going to be the same material from which the contaminant has been removed, or are you going to take good earth from some other place and bring it back? If you are going to put good earth, then all this has to be disposed. So either it will go to a landfill or you will have to treat and dispose it somewhere else. So if you don't have the time to excavate, treat and place back, you will excavate and fill with good earth and treat and dispose after treatment to whatever location from where you took that other earth, or it will go to a hazardous waste landfill for encapsulation within the liner and the cover system. So we have to treat the source, the soil, the pore gas, the pore fluid and the groundwater. One of the methods is excavate and treat. You excavate the source plus the affected soil and dispose in a landfill. Probably going to be the most cost effective, but you are going to lose some of the air space in the landfill. You might want to excavate the soil and do soil washing or heap leaching. Very simply put, if you have got soil which has got contaminants which are soluble in water, pass a lot of water through the soil, the contaminants will come out into the liquid phase and you can use the solid matrix back. You might want to do physical separation. You have got soil which is contaminated. Suppose the soil is made of sand and silt and clay sized material, which is the fraction which is likely to have the contaminant in it? You have a soil which is made of sand, silt and clay, and you find that okay, there is a particular contaminant, which fraction of that soil is likely to have the contaminant? But clay is likely to be most active because one, it is colloidal, it is net negatively charged, so it is always the inerts, the gravel and the sands are not that active. So if you can fractionate it, that means if you can do physical separation, maybe you can discard the clay size portion or it becomes much lesser and you can put it in the landfill, and the sand and the silt size portion you can reuse. So physical separation sometimes helps you separate out the contaminated fraction of the soil from the non-contaminated. Another treatment which is possible for small amounts is after you excavate the material is to incinerate it. So if it has got some, or you heat it, if it's got high volatile organics or if it has got some other organic compounds, you can incinerate it, and that will be another way of treatment. And finally, you may also do bioremediation or biological treatment by using some microorganisms. So one of the ways of tackling contamination of small sites is excavate and treat. Another remediation philosophy is extract and treat. You've got soil which is contaminated, you've got groundwater which is contaminated. The philosophy is very simple. I'll take out the groundwater because I can easily pump it out, and I'll treat it and inject it, or I'll take it out and treat it, inject fresh water. The fresh water will wash the soil. It's like in situ soil washing. In the meantime, I'll treat this water and re-inject it. So you can continue to do the groundwater pump and treat till the water which you pump out is clean, which means that the contaminated groundwater has been removed, you have removed the contaminant, and the groundwater has come back to its original condition. It also means that the groundwater that you have injected is also washed the soil particles, so that if there were any contaminants on it, they have been released into the groundwater, which has been again taken out and treated. So groundwater pump and treat is very often adopted as one of the ways of contamination control. It's not a simple process. It takes years. It may take years in a particular kind of soil. The whole plume has to be sucked out. The whole residual contaminant sitting on the soil has to be sucked out, so it may take years. Soil gas extraction and treatment is relatively simpler. This happens around almost all petrol stations. The vapors of the petrol from the leaking tanks fill up the vadose zone. That means the unsaturated zone always smells of petrol. So you can just extract it using small wells, pump out the gas, inject fresh air, and that is it. So soil gas extraction and treat is also one of the solutions, which is adopted in most of the petrol stations. In some complex cases, you have to do multi-phase extraction. That means you have to separate out the gas and the liquid and the solids and treat each one of them separately. But this is a rare case, so we will not get into this at the moment. One of the philosophies is, can we not transform the material? So can I do in situ oxidation? Can I do in situ bioremediation? Can I do air sparging? Can I do phytoremediation? Can I heat the soil in situ? Can I do in situ electrokinetics? You remember dewatering using anodes? So can you do a net negative and positive charge where the contaminant will come to one of the electrodes? That's in situ electrokinetics. And can you use permeable reactive barriers? The idea here is to transform the contaminant, to immobilize it. It should no longer be water soluble and travel with the water. That's the thought. If you continue with immobilization or transformation, another option which is in situ grouting or deep mixing. You've got contaminated soil. Why don't you use the deep mixing technique using cement? If you can make a cemented matrix of the soil, at least the contaminant will not move forward. So in situ grouting or deep mixing is also a immobilization remediation technique. Of course, the ultimate is in situ vitrification, not yet significant reality, But if you can, either through high heat or through high voltage, convert the matrix into a glassy substance which will entrap all the contaminants, then that is also a technique that we would like to adopt. That means transform the contaminated soil into a glassy, amorphous glassy matrix. So these are some of the remediation techniques which are adopted, for which you will have to use the appropriate engineer, whether it's a chemical engineer or a thermal engineer or a biochemical engineer or a chemistry person, expert. But temporary safety measures while we are doing all this is restrictions in land use, relocation of the people and adopting safety measures, and of course drinking water treatment and actually closing all the groundwater wells from which this material is coming out. I said let's look at pump and treat because this is adopted the most often. So let us say in plan this is the source and this is a contaminated plume. My immediate reaction is let me control this plume from spreading, and I put a vertical barrier all around it. Okay. However, I have to bring this entire area back to its original condition. The source has to go, this has to go. Immediately what I start doing is these red dots can be my groundwater extraction wells. I'll decide what to do about the source. I'm looking at the technologies, but I have to start withdrawing my plume. So I do pumping out of groundwater from the plume. And as somebody suggested that if you pump too much water you may have settlements, then I will also put these blue colored dots are the injection wells. So simultaneously I will be extracting groundwater, simultaneously I will be injecting. In a way, if you look at it sectionally, water is coming in and going out, it's washing the soil also, and it is maintaining the water table, and it is also we are treating the groundwater. So in section, if I let us say this is my groundwater, this is the contaminated groundwater, and my plume, let me say, is here. It's a large area plume. So if I start extracting groundwater, what will happen to my groundwater level? Agree? My groundwater will lower, and I'll be extracting and sending it to treat. So I'm pumping out the groundwater. If I now put in some injection wells, then what will these injection wells do? These injection wells will raise the level of this depleted, and they will try and bring up the level back to its original position. So I have extraction wells which go to pump and treat. After treatment the water comes in, or in the beginning you are sending in fresh water. And remember, so now you are sending in the water here and you are taking out the water from here. So there is in a sense flow taking place like this, right? So clean water is traveling from one well to the other. It's also washing the soil in between. So that is what is happening in your pump and treat. So you monitor this, and the situation is, as I said, all the water is going out. You put a slurry wall, so it may be a hanging wall. These are the zones of influence of your wells, okay? And they are overlapping zones, and these triangles are your injection wells and the circles are your extraction wells. Over a period of time, what will happen is the plume will break up into small pieces. That means this is now back to fresh water, or drinking water, and the contaminated plume is here, here, and here. And gradually all this plume will become smaller and smaller, and the injected water will In the meantime, you have also removed your source. So say several years hence, you will find that you can bring this site back to its original condition. So pump and treat is a very often adopted methodology for areas where groundwater contamination has taken place. The other technique is soil gas or vapor extraction. I told you volatile organic compounds in unsaturated soils, this is the cleanup. You install small diameter wells, apply a vacuum to those wells, the gas vapor will come out, you send them to a treatment unit, you inject fresh air with injection wells, and of course the arrangement is very similar to pump and treat. You will come across the word air sparging. Air sparging is used when LNAPL and DNAPL hydrocarbons are mixed with the water. They may be floating on the top, they may be in the middle, they may be at the bottom. But if you send air into it, these will volatilize. And then you can extract that air and the vapor will come out. So air sparging, please use soil gas vapor extraction is for the vadose zone. Okay? You can't extract gas from the saturated zone. Whereas air sparging is from the groundwater zone. So air sparging is the injection of air under pressure into the contaminated groundwater for in situ volatilization of the petroleum hydrocarbons from the mixed state to the vapor state. So you send in the air and then you extract the air, and along with the air out come the fumes of the hydrocarbons, and eventually the entire hydrocarbon volatilizes and is cleaned up. How would you wash soil? Okay. So I have a small amount of soil, and my contaminant is water soluble. I have excavated it using, let me say I have got a soil of the size of half this room. Is that a good volume? So how will you wash the soil? I can use an excavator to dig it out. So I've dug out the contaminated soil from this site, and it's all come out to you. How will you wash the soil? Any thoughts? If the soil is sand, I'll put it in a tub of water. Anything scares you about putting sand in water? Oh, I'll make a big tank of water. Or I'll make a tank of water and put it little by little. What will happen? The contaminant will come into the water because it's water soluble. Yes? All of it may not come out, but some of it will come out. Sand will settle very fast. You will decant the top, treat it, and you are not sure whether everything has come out. Take the sand again, put it in some more water. You will continue to do this till in the decanted fluid there is no contaminant. You can do it with sand or gravelly sand or sandy gravel because it settles in a few minutes. Now just take the opposite. I have silty clay. What will you do? You put silty clay in the tub of water, then you will wait. Why? You want it to settle, and then you will wait, and you will wait, and you will wait, because it doesn't settle so fast. So treating coarse grained soils is simpler than treating fine grained soils. Okay? So if I have a clay silt or sandy silty clay, one of the ways to do it is to make a heap. The soil was of this quantity, and I can do drip irrigation from the top, and the fluid will go through slowly and it will come out at the bottom. Bottom I will put a drainage layer, and I will put a liner so that nothing goes. So depending on the type of material you have, you may do heap leaching. You may do drip irrigation at the top. But basically, you have to allow water to percolate. It may take several months, but that's fine. Eventually, you will get water which is not contaminated, which means your soil has got washed. If you are in a great hurry, maybe you would like to fractionate your soil. Why? Because there is a chance that the contaminants are only in the fine grained. So, you do sieving, take out your coarse grained soil. Coarse grained soil will settle very fast, it will be available for you very fast. The fine grained soil may require some treatment. So, suppose 70% of the material is coarse grained soil, so half your problem is solved, because coarse grained soil will come over the sieve. You can wash it very quickly, it settles very quickly. The fine grained soil is something that you have to tackle. Now, are you going to heat it and burn it? Are you going to do heap leaching? Or are you going to add some chemical to it? Are you going to acidify it and release the contaminant? That's a separate problem. So, in a sense, soil washing can be done in a container or a heap. Particle fractionation may be done before the washing. Soil is mixed with excess water to release contaminants. The solution is decanted or filtered. If you are going to have too many fines, you are going to have problems. Then the soil is arranged in a heap on impervious base, overlain by bottom drain. Allow water to percolate through the heap, drip irrigation, and release the contaminants. Sometimes you may add a little chemical to the water, which is a solvent which will help faster release of the contaminants. That will depend on the chemistry of the problem. So, you can use solvents to release the contaminants also. This is actually like a mining, getting like a mining technique. In the mine, you are trying to get the ore to come out of 99% of the rock. Here you are trying to get the contaminant to come out of a matrix which is full of soil only. So, you continue till the leachate of the soil meets the required standards. So, that is the concept of soil washing. Any question which bothers you about soil washing? Bioremediation. Well, basically you use microorganisms to degrade and transform organic chemicals in contaminated soil. And usually when you have petroleum products or hydrocarbons or pesticides, if you have overdosed it, you can introduce microorganisms. This can be done ex situ or in situ. Ex situ is much better because you can do it in a controlled environment. You can control your temperature, you can control the moisture, you can control the relative humidity, you can control the available oxygen. So, better you bring out the soil, excavate it and do it in a containerized manner. However, at some locations bioremediation has been done in situ as well. And there you need very hardy microorganisms, but you are able to do it in situ as well. The processes when you are dealing with vadose zone are separate, and the processes when you are dealing with the saturated zone are separate. Please remember, these are different biological processes. All bioremediation exercises are not successful because proper conditions, you may start with the proper conditions, but you may not be able to maintain them. So, temperature, oxygen, moisture, pH, etc. are very important for the microorganisms to thrive and be effective. But they have been found useful for contamination which has been caused by petroleum products and by pesticides. A subset of bioremediation is phytoremediation. Phytoremediation is plants. So, I will just quickly do that. In phytoremediation, you use plants for remediation, and the concept is of bioaccumulation. What happens? Roots of specific plant species will uptake not the contaminants, but the whole solution. As the roots uptake the water, these contaminants will also come into the root and they will get deposited in the tissues of the plant. So, you do bioaccumulation of the contaminant inside the plant. Water will evaporate, salts will come and accumulate. So, contaminants are removed from the soil and accumulate in the plant. In the end, you are supposed to dig up the plants and you may want to incinerate them, or you might want to do some activity which makes you, when you incinerate them, you will get ash. The ash will have the contaminant, and that will be very small, and then you can stabilize it and put it in a hazardous waste landfill. So you remove the plants, incinerate them or treat them or biomine them. Some people want to mine the stuff from the plants as well. Remember two things: plants have a limited capacity, process is slow, and they only work up to the root penetration depth. Recently we were involved in a case where one huge distillery in Western India has contaminated the soil and the groundwater, including that in the fractured rock below. And I think the depth of contamination is about 20 meters. And you get this very dark colored, dark tea, black tea kind of liquor or contaminated water in the wells nearby. And phytoremediation was proposed by one of the research institutions. But I know of no plant in which the roots will travel 20 meters into the ground to pick up contaminants. So phytoremediation is the near surface problems can be solved. Or you have to pump out the leachate and then put it into an artificial bio phytoremediation pad that you might create. So some heavy metals, pesticides and solvents have been mitigated by phytoremediation, which works well for only the top meter or less of the soil in the top. So these are some of the methodologies which are used. These are evolving all the time. And success is limited. Pilot studies are a must before you undertake them. So look at all the alternatives, look at the one which has worked in the last 5 years, test it on your soil. If it works, and adopt it on a large scale. It's very, very expensive. I'd like to close this by talking about a case study. Before I do the case study, because this is about a vertical barrier. Any questions on remediation? Two important things. As a geotechnical engineer, it's our responsibility that when we do extraction and injection, all the soil feels it. That means water is coming out but from overlapping zones of influence. It's not that one well is doing well, second well is doing well, you will come back and say, sir, my water quality is fine, but the zone in between, which is not in the zone of influence, still has some stuff which is harmful. So our design is a dewatering design with the zone of influence overlapping. When I am injecting, I have to ensure that the injection liquid reaches everywhere into the ground. So that is our role. And if somebody comes and says that I would like to do in situ grouting, and I have to tell him, look, in clay you can't do in situ grouting. Why? Somebody says, no, I have got a beautiful culture. I've got this bioculture. All that we have to do is introduce it into the ground, and these microorganisms will spread everywhere. So you say, okay, I've got a 15-meter deep contaminated zone. So it says, okay, we will inject it at every 1 meter or 4 meter depth. You have to tell him it's clay. I can't even inject water into clay. You can make a borehole. I can go and place this bioculture at that level, but how is it going to travel? So as geotechnical engineers, you can say, fine, if it is sand, yes, I can inject it, I can pump in, I can make a well, I can pump in the water, but if it is clay, it's not going to go. You can do hydrofracturing. You have done that in ground improvement, like make a root-like structure. But then your design should be like that. Your spacing of the wells has to be very close together if you are going to have overlapping hydrofractured points. So as geotechnical engineers, it's our role that we must be able to tell. You see, in situ injection and in situ grouting is so magical. I can take cement, I can inject it into the ground, and I can make soil into rock. How does it sound to you? I can make a hole, I can take some quick fix, Fevikwik, I can inject it into the ground and my whole soil will become very hard like rock. The point is, you try and inject it, it's not going to go into the soil. Grouting only takes place in gravels and sands. It doesn't take place beyond that. You use some PM9 or some other grout, chemical grouts, they also have limitations in
penetration.
And in any case, you are not able to give a uniformly cemented matrix where your hole will be, maximum cement will be around the pipe, maximum cementitious material. As you travel further away, the cementitious material will be less. How do you assure me that it's equal everywhere? Then the automatic choice is excavate, pulverize, mix, and let there be intimate contact between the chemical and whatever it has to react with. So these are the things where geotechnical engineers have to play an important role. So I'd like to finish off with a quick case study on vertical barriers. This is a tailings pond in one of the western states of India, 1600 meter, 1.6 kilometer long and about 0.6 kilometers wide. Tailings were being placed in it till one day it was told by the pollution control board that look, your lead content is high. This is a hazardous waste pond. It doesn't have a liner. Please do something about it. There was a 5-meter high embankment at one end, 9 at the other end. Tailings had only filled up to 2 to 3 meters. There was a lot of capacity which was available. That's the tailings pond. That's the tailings pond. This is the slurry water. One of the consultants gave the solution that all right, now this is hazardous. So let's cap it and then let us fill the ballast tailings on top. This will work as a cover and a liner for the new tailings and cover, and nothing will go through. But the problem was, if you put a layer here, with time these tailings which are hydraulically deposited will settle and this will all have seepage paths and it would not work. So this work got referred to us, and after looking at various options, IIT suggested that why don't we continue to put the tailings but ensure that nothing escapes the pond. You know, water was seeping through the embankment and below also. So let's put vertical cutoffs, and then when the tailings reach the top, we'll cap it. So we started doing the investigation. First site investigations were done and this kind of result was obtained. There was, you know, soil at the top and then rock at the bottom. Soil at the top, rock at the bottom. This is some more, and the generalized soil profile was like this. There were two types of soil, soil layer A, soil layer B, then rock layer A, rock layer B. Rock layer A was disintegrated rock with high permeability, and rock layer B was the actual impervious rock. So the thickness of this was 2 meters to 6 to 8 meters, and those were your tailings and these were the embankments. So we looked at the types of soils, soil layer A, soil layer B, rock layer A, rock layer B, tailings. We studied all the engineering properties. Tailings had a permeability of 10 to the power of minus 4 centimeters per second. Soil had a permeability of 10 to the power of minus 5. Rock layer A had very high pump-in test, 78 lugans, very high. But rock layer B was impermeable, 1 to 2 lugans was the value. That means the inflow was very low. So this was a good impermeable rock. So it was proposed that in the soil we'll make a vertical cut-off wall and we'll make a grout curtain in the rock up to the lower rock level. And this was proposed soil bentonite cut-off wall and cement grout curtain 15 meters into the rock. There was no way you could make the wall. You can't excavate that rock with a trench cutter. And we started working how to make this. The required permeability of the wall was 5 into 10 to the power of minus 7 centimeters per second, not 1. For a vertical wall, the required permeability was 5 into 10 to the power of minus 7 centimeters. We could use the excavated soil, we could use the local top soil. There was a borrow area about 20 kilometers away. These were the three options. Okay? all of them were plastic materials. Excavated soil had too much gravel, so it went out of the reckoning for making the vertical wall. When I took the local soil and the borrow area soil, the permeabilities were 10 to the power of minus 7. We were very happy. We wanted 5 into 10 to the power, but this is for compacted soil, Proctor compaction. In a cut-off wall, you are not able to compact the soil. It is just sent in by slumping. And then we added bentonite, 5%, 10%, and really the permeability is decreased. And further, from the borrow area soil, the permeability went to minus 10 to the power minus 8. But we needed high slump material. So, with local soil, when we were adding 30%, slump was 8. But when we had 35%, slump was near 16. So, this was good. But because we were using such high water contents, the permeability was becoming 10 to the power of minus 6. With compacted soil, the permeability was 10 to the power of minus 7, but not here. Similarly here, when I used 40, 42%, 45%, my slump was 15 or 13.5, but permeability went up. So what we did was, we said, all right, we will use local soil plus 10% bentonite and borrowed area soil plus 10% bentonite, and let us see what the permeability comes for high slump material. So to local soil plus 10% bentonite, if I add 40% water, slump was 12 to 17, and permeability was acceptable, 1.4 into 10 to the power of minus 7. Similarly, for borrow area soil with 10% bentonite, when I am using higher water content, 50 to 55% water content, I was getting 14% slump and I was getting the requisite permeability. Now comes the question which was asked, that what happens to the stability. The question that was asked by somebody was that when you make these vertical, I have this embankment, one of the embankments, I am going to make my trench here, and then I am going to do grouting. Okay? Now when I make my trench here, I am going to fill it with slushy, loose, soft, clayey material. So, is this it? Can there be this is a vertical cut of 8 meters. So now we have to make this stronger. So soil, it's a mixed design problem, very simple. You took soil and you added bentonite to get the low permeability. Now you take the soil and the bentonite and add cement to get good strength. That means as deposited material will get strength not from compaction but from the cement. So the next set of tests that we did was to add cement. So let us look at local soil plus 10% bentonite plus 10% cement. Okay? And after 7 days, I was able to get a strength of 130 kilonewtons per meter square. And this I was able to get a strength of 71. So this is the mixture that we used. This was the mixture that we finally used for the purpose of preparing the vertical cut-off wall. And if I could show you, the permeabilities were acceptable. The requirement was 5 into 10 to the power of minus 7. You see, when you add cement, what happens? Does the permeability go up or does it go down? Cement will granulate the soil, agglomerate it. So permeability goes up. So you had soil, you added bentonite, the permeability went down. I want you to see these values. Local soil plus 10% bentonite at high slump was 1.4 into 10 to the power of minus 7. Borrow area soil was 1.8 into 10 to the power of minus 7. When I added cement, this went up to 7 and 5.5. However, this was acceptable for us. Both we accepted and we got the strengths that we wanted, and now this material became stronger than the soil around it. And therefore, there would not be a problem of instability. So we would not cut the wall in one go. We would make sections of this wall and then we would put in this material such that limited sections were exposed, and then it would set, and in about 7 days it would have good strength. So this was proposed, and in comparison to that 1.6 kilometer by 600 meter liner which was proposed, it was very expensive. The vertical cut-off wall was less expensive, and this is what was adopted. So the process of design was a mixed design, and the process of implementation is another issue, because you have to do intimate mixing. Everything has to be mixed in a plant outside, because you are now mixing soil with bentonite with cement, and then you have to place it back into the vertical cutoff wall. So any questions on this, either on the case study or on the remediation that we did? But this is the way one has to proceed, like a mixed design, to be able to get a correct mix for soil clay walls, soil bentonite walls, or soil bentonite cement walls. So we'll stop here. Have a good day. All the best.